And now one more theorem that says that if we have a set E in a metric space X and P is a limit point of E, remember the notion of limit point, that means there is a sequence Pn in E such that P is the limit point for that sequence. Okay, so again, for every limit point of E, let's call this limit point P, there must be a sequence that converges to that limit point. It's a bit the opposite problem. Usually we say, given a sequence, what is the limit? Here we are saying if we have a limit, that is because there is a sequence that converges to it. Some sequence. There could be many sequences. Now the proof. So here we use the definition of limit point, right? So here for each integer n, okay, there exists some point Pn in E such that the distance between Pn and P is less than 1 over n. This is just the definition of limit point. Okay. Now, I was saying in the definition of limit point, we are told that for every neighborhood of the limit point P, there has to be some point in the original set in E that belongs to the neighborhood and it's not P. Okay, that's what this condition means here. We are taking neighborhoods written in this way: the distance less than 1 over n. This is a neighborhood of radius 1 over n of the point P. These are all different ways of saying the same. Okay, so once we have this, notice that given epsilon bigger than 0, we can choose capital N such that n epsilon is bigger than 1. Okay, did you recognize here the Archimedean property of the real numbers? We can choose that n because of that. Now, if n is bigger than n, that sounds silly. If lowercase n is bigger than capital N, then it follows that the distance between Pn and P is less than epsilon because we knew that it was less than 1 over n, okay? But because n is bigger than capital N, that is less than 1 over capital N, and that is less than 1 over epsilon, okay? Because we were assuming n epsilon bigger than 1. Now, if you were wondering why did I pick n epsilon bigger than 1, is because I wanted to force that 1 over capital N would be less than 1 over epsilon. So I actually did this line first. And once I saw what I needed for capital N, then I went back and said, well, N must be like this. Okay. And once I have this, that, wait. Oh, no. Sorry about that. Not 1 over epsilon, but epsilon. Once I have this, that the distance is less than epsilon, Pn to P, then by definition, Pn converges to P. And this completes the proof.